Swayam Prabha. Digital India. Educated India.
So, welcome back. Today we will study three-phase multi-winding transformers. I mean, basically first we will study multi-winding transformers, then which is a single phase concept, and then we will graduate that concept further to the three-phase level. So, for let us say that to multi-winding transformer means basically usually what we have seen in a single phase transformer, what we have seen is one primary, one secondary. So, you have two windings. So, it is called a two winding transformer, but you could have why do you need to have only one winding? You could have many windings. So, in fact, here I have got n windings which are coming on this laminated core, and you can imagine that it is this circuit is getting closed from somewhere here below. This is like a single phase 3 winding transformer. So, let us draw a very simple sketch. This is my first I should have a core, so this becomes my core. Now, usually I have one primary, right, then I can have, I will not put the dot, I will leave it to you to put the dot, find out how the dots come. So, let us say this is V1, let us say this is V2, this is V3. So, this will become a single phase 3 winding transformer. Yeah, so this dot will incidentally come here, and if I rotate the right handed screw with current entering from this terminal, so I will get the polarities coming in the flux coming in the same clockwise direction. So, therefore, these will be the 3 V1, V2, V3. Now, let us say this has turns N1, this has turns N2, this has turns N3. So, the flux linking all the 3 circuits is same, assuming a ideal core, completely no leakage and so on and so forth. That is how we start building this. So, we will get, so everything is a mutual flux therefore. So, V1 is d phi m by dt. I just wrote m for to indicate mu 1. I think I should use, I will use just phi, small v 1 let me rub it. This is yellow is my flux line. Just a minute. it's not yeah, just a minute. Yeah, this is okay. The flux lines go like this, come back like this, we take a darker color. So the flux lines are going like this, like this, like this. Of course they are not right angled, so should probably be showing it. Something like that. Smooth lines. Line should be smooth with smoothly. Yeah. So V1, what is this V1? This is instantaneous voltage. Remember, this is the instantaneous voltage, because whenever I use d phi by dt, it has to be instantaneous voltage. V2 will be N2 d phi by dt, and V3 will be N3 d phi by dt. Why? Because there is no leakage flux. So, the same flux is linking all the three. So, you will get V1 is to V2 is equal to V3, these instantaneous ones are in going to be proportion to N1 is to N2 is to N3. And if you want to talk of phasors, what you should do? You should replace, I mean, you can directly say that the phasor voltages, because the V1, V2 and V3 are all in phase. So, their phasor value is going to be just the peak value, which is in the ratio of N1 is to N2 is to N3. So, then you will divide it by 1 by root 2 to get the RMS value, and that RMS value is nothing but the magnitude of the phasor voltage. So, therefore, V1 is to V2 is to V3 will be equal to N1 is to N2 is to N3, and because these are positive integers or real numbers. So, therefore, these phasors will be V1, V2, V3 will be in phase. So, if this is drawn as V1, then say this could be V2 and say this could be V3. I mean, in this particular case, the way I have drawn it here, this is like a step down transformer, and of course, ideal because there is no leakage flux and so on. So, this is the same, this is the basic idea, and you could have actually n winding transformer. So, V1 is to V2 is to Vn will be in the ratio of N1 is to N2 is to Nn. These are capital letters. So, therefore, they indicate phasors, and the turns ratio are going to be similar. Now, the next important property that I want to prove is this N1 I1 equal to N2 I2 and so on summation up to N1 Nn In. So, my current, just look at my this current, this is the magnetizing MMF, this is the magnetizing MMF N1 I1, and because this current is coming out of the dotted terminal. So, therefore, N2 I2 is the demagnetizing MMF. This similarly N3 I3 is also demagnetizing MMF, and Nn In is also equal to, is also the demagnetizing MMF. So, the difference between the magnetizing MMF and the total demagnetizing MMF. So, I will have to sum all of them together, should be equal to the MMF which is required to set up the flux in the circuit. So, what I am trying to say is N1 I1 minus N2 I2 and so on up to Nn In will be equal to flux times of the reluctance of the circuit, but because it is taken as an ideal circuit right now. So, the reluctance is going to be equal to 0. So, therefore, this goes to 0, and for an ideal n winding transformer, we will therefore get the MMF balance principle will turn out to be N1 I1 is equal to N2 I2 is equal to N2 I2 plus N3 I3 and so on up to Nn In. So, if you had a 3 winding transformer like this, which I had shown here, and the currents are, this current is let us say primary magnetizing and these currents are all demagnetizing, then I will get N1 I1 is equal to N2 I2 plus N3 I3. So, this is the governing equation that I will get in this particular case. Good. Now let us look at the third important thing, the power balance. So, this is the MMF balance, this is the same mutual flux link, the same flux linking all the coils, EMF per turn is therefore the same everywhere, EMF per turn is just d phi by dt, which is same everywhere. The third is power balance principle, we directly written it for complex power. So, that will automatically also apply for the real power, also we can separate it out, and the reactive power also we can separate it out. So, let us do that. Let us do that. So, I have N1 I1 from the MMF balance principle, N1 I1 is equal to this plus N2 I2 plus N3 I3 and so on up to Nn In. Now, let me divide, let me write this as N2 by N1 by dividing it by N1 plus N3 by N1 times of I3 and so on Nn by N1 times of N1. Now, let me take the complex conjugate of whole of this equation. So, I will get complex conjugate here and I will have to take complex conjugate of this term, complex conjugate of this term and complex conjugate of the each and every term. But because N1 and N2 are integers, usually real numbers, so their complex conjugate will, that is a real number. So, therefore, its complex conjugate is going to be the same thing as it is. So, the actually complex conjugate operator is going to only come on these sides. So, when I take complex conjugate values, I will get this as N2 by N1 times of I2 star plus N3 by N1 times of I3 star and so on up to Nn by N1 times of In star. So, now what I can do? I can write for N2 by N1, I can write it as V2 by V1, correct, because V1 is to V2 is same as N1 is to N2. Then I can write this as V3 by V1 times of I3 star and so on. I can write this as Vn by V1 times of In star. So, therefore, I will get V1 I1 star. Now multiply completely, this is my I1 star. Now, multiply this complete equation by V1. So, left side will become V1 I1 star and each of these V1s will cancel on the right hand side. So, I will get V2 I2 star plus V3 I3 star and so on up to Vn In star. So, now you can write this as P1 plus jQ1 is equal to P2 plus jQ2 plus P3 plus jQ3 and so on up to Pn plus jQn, or P1 plus jQ1 is equal to P2 plus P3 up to Pn. This is separating the real part and this is separating the imaginary part. So, now therefore, the real part of the left hand side should be equated with the real part of the right hand side, imaginary part of the left hand side should be equated with the imaginary part of the right hand side. So, we will get P1 is equal to P2 plus P3 up to Pn and Q1 is equal to Q2 plus Q3 up to Qn. So, this becomes the proper for ideal transformer, proper real power balance equations, whatever power in watts or megawatts comes from the primary side will be dissipated or moved out from the secondary side. Whatever reactive power MVAR or VAR comes from the primary side, the same will be moved out from the other side, the secondary, the tertiary. If it is 3 winding, usually we call them as primary winding, secondary winding and tertiary winding, but here there are n windings. So, you will have this coming, but the power balance and the MMF balance equations look very similar in a transformer, ideal transformer, like what we get in the KCL. So, that is the beauty of the device. You do the scaling of the voltages and the current levels, but you really do not seem to lose anything. Whatever comes in flows out, whether it is active power or the reactive power. Now, let us take a example, a 3 winding 3 phase transformer feeds power from a 3 phase generator to both 400 kV grid and a local industry served at 132 kV. The 3 phase transformer is made up of 3 identical single phase 3 winding transformer units connected in star grounded configuration. Determine the required transformer ratios A12, that is 1 to 2 winding, A13 which is 1 to 3 winding. So, what is told here is just so this is just drawing a sketch for you. Okay. So, again so this is primary, this is secondary, and let me draw the tertiary in a different color, but on the same same limb. Okay. This is the tertiary. Now, this is one single phase transformer, right. So, I have 3 such single phase transformers. So, this becomes my So, this becomes my phase A, phase B and phase C transformer. A, R, Y, B, P, C can be in the blue color. So, no problem, C is in the blue color. And these are connected in star grounded configuration. So, what I will do is slightly take a thicker pencil . Then make it even more thicker, yeah, and this is grounded here. This is a basically connector wire. This is A, yeah, B, C, and similar thing is done for the this. So, this is primary I have done V1, V2, V3. Similar thing is being done for the secondary and the tertiary. So, let me just take this a bit out. Let me copy this. Okay. So this is the P side, this is the secondary side, again A, B and C. And the tertiary will also give you A, B and C. So, I will just copy this again, duplicate it, bring it, duplicate, bring it here, change the color to show that this is the third winding, and I am sorry, we will take the blue color. So, I get again A, B and C, and this is also rounded. So, this becomes, how many windings are there now? 1, 2, 3, 4, 5, 6, 7, 8, 9. So, 3 phase 3 winding transformer will have 9 windings, 3 phase 2 winding transformer will have 6 windings. So, this is my configuration, and what is given to you here? A 3 winding. So, it is shown, schematically it is shown like this. Normally, we show only these 2 windings like this, but here schematically we want to show for a 3 phase system. So, A, B, C 3 wires, here also A, B, C 3 wires, here also 3 phase generator. So, A, B, C 3 wires, and this is the first winding, the secondary winding and the third tertiary winding, and everything is multiplied by 3. So, it is actually for A, B, C and C. So, this is how the pictorially this example has been shown. A 3 phase, a 3 winding 3 phase transformer feeds power from a 22 3 phase 22 kV 3 phase generator. So, the generator is at 22 kV, it is grounded, 3 phase grounded, and it stepped up to 400 kV. One winding is stepping it up to 400 kV, means it is going to go far away. When you step it up, you actually cut down the current and then take that winding, take that transmission line for a far away distance, then step it down and again use it. So, this is being moved far away, and a local industry load served at 132. You do not need to, because the wires are not going to be very long, the drop in voltages and the resistive drops are not going to be very large. So, you really do not need to step it up to this voltage level. But I have a generating station, I have a local load which could be the generating station's load itself, or it could be some small township load which is around that generating station, or a industry, as it is told here, it is a industry load. So, I serve that load and I send it far away. So, the advantage now is that whole of this job, that one generator, one local load and one load which is to be served at a very long distance through a transmission line, all are managed through one single 3 winding 3 phase transformer. So, you see the utility of this is clear to you. The 3 phase transformer, is made up of 3 identical single phase 3 winding transformers units, which I just drew below in star grounded configuration. determine the required transformation ratios from primary to secondary and primary to tertiary. So, what is the primary voltage phase to neutral? 22 kV is applied on the primary. So, it becomes 22 by root 3, which is 12.70 kilovolts. The secondary voltage, that is the 400 kV transmission line, 400 kV transmission line. So, 400 by root 3, which is 230.95 kV, and then the industry load is at 132 kV. So, therefore, 132 by root 3, because it is all star connection. So, therefore, the phase to neutral will have that root 3 factor, which is 76.21 kV. So, primary to secondary A12 is going to be the ratio of 12.70 is to 230.95, which is 0.05499, N1 by N2 is equal to V1 by V2, and the turns ratio A13 is similarly V1 by V3 phase to neutral, N1 by N3 is equal to V1 by V3. So, what is it? We are required transformation ratios. So, this is going to be 0.16664. So, let us continue the example. Now, what I am doing is I am giving you loading levels on the secondary and the tertiary side. So, there is it is not it is a proper working transformer. There are some megawatts and MVRs flowing on the secondary and the tertiary side, and then we will find out what is happening on the primary side. So, let us see. Consider the transformer of figure 1, that is the same transformer. 600 megawatts and 150 MVAR are flowing out on the 400 kV side. The local demand from the 132 kV bus, this bus actually basically is a 3-phase connection. Many times it is called as bus because it comes from the abbreviation bus bar. It is like a copper bar on which different wires come and connect. So, that is why that node or bus, these are some common phrases that is used. The local demand on the 132 kV bus is 99 megawatts. At unity power factor, find the currents and powers in all the 3 windings. So, V1 is basically N1 d phi by dt. D phi by dt you can when dealing with phasors you can replace it by j omega, not that I really need it, but V2 will become j omega N2 phi and V3 will become j omega N3 phi. So, you have this V1, V2, V3, they are all going to be in phase, this I have already explained to you, and with respect to the phasor, all of them are going to have a 90 degree j omega, means a 90 degree lead will come here. So, this is my flux phasor, this V1, V2, V3 are my voltage phasors. Now, I1 has a reactive load of 600 megawatts and 150 MVAR. So, therefore, it will give, it is a lagging power factor load. So, therefore, I1 is going to be lagging and I3 is given as 99 megawatts at unity power factor. So, therefore, the I3 is going to be in phase with V3. So, therefore, this is what is going to happen, and MMF balance principle will basically bring out that the resulting I2 will also have a lagging power factor, mainly due to this particular color, this particular I1, and of course, this figure has not been drawn to scale. Now, because I have 3-phase load of 600 megawatts and 150 MVAR, so therefore, 600 plus 150 divided by 3 will give you 200 plus J50 megawatts and MVAR per phase of the S2. This is on the 400 kV transmission line, and 99 megawatts at unity power factor, this is the industrial load on the 132 kV side. So, again per phase if you look at it, it is 99 plus J0 by 3, which is 33 plus J0 megawatts and MVAR per phase. Now, secondary MVA P plus JQ is 200 plus J50, J50. So, that should be written as V2I2 star. 33 plus J0, which is the apparent or complex power on the tertiary side, should be written as V3I3 star. So, now can we calculate I2 from here? Yes, you take a star of whole this. So, you will get V2 star I2 is equal to 200 minus J50, but V2 you know how much is V2? V2 is 230 kV, 230.95 kV, and all of them are at an angle 0, they are all in phase and are in aligned with the reference phasor. So, this is also angle 0, this is also angle 0, this is also angle 0. So, when I did V2 star I2 is equal to 200 minus J50, and then I divided this whole thing V2 star, I bring it down 0, because it is a real number, the complex conjugate is going to be the same. So, therefore, I2 will become 200 minus J50 divided by 230.95, which is effectively 0.866 minus J 0.216, which is lagging current, because this is the real part and this is the lagging imaginary part, and so this is the I2, this is the I2 real, this is the I2 imaginary. So, you have a 14-degree lag, 0.8925 unit kiloamperes. Why kiloamperes? Because numerator is in MVA and the denominator is in kV. So, MVA divided by kV will give me a current in kiloamperes per phase. I3 per phase load is, to calculate I3 per phase load, it should be written here, though it is plus J0 and minus J0 are same, but to be consistent with my notations, I would prefer to write this as minus of 33 minus J0 to indicate that a complex conjugate operation has been done, divided by, because these are angle, these numbers are all angle 0. So, therefore, this voltage on the tertiary side was 76.21. So, therefore, angle 0 is also 76.21, and so this will also turn out to be therefore 0.433 minus J0 kiloamperes per phase, which is basically as I had shown here in phase with V1, V2 and V3. So, now we have seen the power balance principle, complex power balance principle. So, V1 I1 star will be equal to S2 plus S3, but how much was S2? S2 was 200 plus J50, S3 was 33 plus J50. So, when I do S2 plus S3, I will get 233 plus J50. So, when I do 233 plus J50, this is V1 I1 star. So, again take complex conjugate of whole of left hand side and the right hand side. So, this will become 233 minus J50. Now, divide by V1, but V1 is 12.70, V1 star, actually you are dividing it by V1 star, but V1 is 12.70 at an angle 0. So, V1 star is also basically 12.70 at an angle 0, which is just a real number 12.70. So, you get 18.346 minus J times 3.937 or 18.7 at an angle of minus 12.11 degrees kiloampere per phase. So, as I had indicated to you here, this I1 will create a lagging power factor. So, this completes a very nice simple application of a 3-phase winding transformer. So, now I am going to introduce to you a very special type of transformer known as 3-phase ZigZag winding transformer, 3-phase ZigZag transformer connection. I would say that this is a specialized connection and though the analysis is not really difficult, that is why I have taken it up for discussion here, but application of it is very specialized and probably needs more maturity than what we have in this course at this point of time. But the transformer connection is quite straightforward and we can understand it with ease. So, I will introduce you the zigzag transformer connection, and you will learn more about it later on in power systems and power system protection course. But you will get introduced you will understand the apparatus here better. What I am trying to say, you will understand the apparatus here better, and you will understand the application better sometime in future. So, this is basically you take three winding transformers. So, I have like one 3 winding transformer here, another 3 winding transformer here, and the third one, and I have for the ABC or RYB phases, the color coding I have appropriately already given. Now, in these transformers, usually these two secondary transformers are of identical ratings. So, windings are of identical ratings. So, for example, in this example, I have rated this winding 1 for 1000 volts and winding 2 and 3 are rated for 500 volts respectively, and they are interconnected in the primary of them will be interconnected in star connection, which you know. So, you do not have to worry about that. The primary star interconnection is very straightforward. This to this will be grounded, this will go to A, this will go to B, this will go to C. The funny part or the difficult, I won't say difficult part, funny part, interesting part, whichever way you want to put it, non-trivial part, whichever way you want to put it, that happens in the interconnection of these secondary winding. There is, you do not have here terminals for tertiary things, you only have A, B and C on the primary side, and you have A, B and C on the secondary side. So, if you look at it from outside, it is just like a 2 winding 3 phase transformer, but it is built out of 3 single phase 3 winding transformers. So, that's the interesting part. So, that means these windings here in some sense get interconnected, as I have shown here, to bring out only one output terminal later on. Why we do it? We do it for grounding. I mean, especially if you have ungrounded systems, there may be problems of carrying third harmonic, sixth harmonic, triple N harmonics, ninth harmonics, and we want to give them a way to go to the ground, and we do not want to give way for other things to at the same time. We do not want to create a for the normal balanced voltages, we do not want to show a impedance path to the ground, otherwise significant current will start flowing. Suppose let me sort of say that suppose this was not there, let's try. Suppose this part was simply not there. Imagine that this is all not there. I will have to rub it later on, that is going to be a bit of a problem, but it is okay. Suppose this part was not there, and I said I have this one side which is ungrounded. So, there are safety issues, then there are issues like I cannot have the ground some of the current, if there is a ground fault, you will see that later, and the currents have to flow to the ground. So, some conductor has broken and fallen down, then I am not able to provide path, closed circuit path. A conductor has broken, fallen to the ground, but this side my source is ungrounded. So, the current cannot flow, and that is a very dangerous situation, because nothing will trip and then somebody goes and touches the wire, then he will create the short circuit path, and then there is a person can die, and then the fault current will flow through him, something like that will happen. So, we need to provide some kind of grounding. So, for each phase you connect, say, these three primary cores of the transformers, they effectively becomes like inductors, reactors, inductors, and ground it. Then what will happen? Because of the leakage impedance, there will be some leakage impedance, let us say 1%, 2%, then a huge amount, 10%, let us say, then a huge amount of current will flow here to the ground, though it will sum to 0 because of being balanced, but each one of them will be carrying a large amount of current. This situation is unacceptable, because then the whole current profile in the system, in the wires, it has gone haywire because of this ground currents. We have connected the phase to ground through a leakage impedance, and this has created a problem. For the time being, assume these windings were just not there. So, you had three reactors basically on phase A, phase B, phase C. You created a ground out of them and connected it. Then these reactors, according to their impedance, leakage impedance or designed impedance, usually it is 10% on the rating, it will draw large amount of current, and then that is not what we wanted to do. We just wanted to provide some kind of a protection application. So, therefore, such simple connection will not suffice, and we have to resort to what is known as a zigzag connection to provide for specialized applications where otherwise the system is ungrounded, and we want to provide a ground, or we want to provide path for the triplen harmonics to flow. We create this zigzag connection. Now, this is motivation, you will learn much more about it later on. This is just a motivation for you. Now, how do we interconnect the windings? So let us see why do we call this as Z. For this, red is the A phase. On the secondary side, this is let me call this as, though I have this is okay, let it be like this only. So, on the secondary side, what I have done is this winding is one of the secondary windings. Magnetically they are on the magnetically these three windings are perfectly coupled. So, the same flux flows through it. So, V d phi by n d phi by dt is same except for the number of turns. So, therefore, this if this is V1, then this will be V2 and this itself will be V3, because it has having same number of turns. So, now what I have done, so if I apply 1000 volts here, let us say at an angle 0, I will get 500 volts 0, I will get 500 volts 0 here. And similarly, if I apply 1000 volts at an angle of minus 120 degrees here, I will get 500 minus 120 degrees here, and I will get also 500 minus 120 degree voltages here. And if I apply, this is the C phase. So, if I apply 1000 leading 120 degrees, then I will get 500 leading 120 degrees volts here and 500 leading 120 volts here. Now, look at what I have done on the secondary side. So, this side is my primary side of the 3-phase transformer. This is the secondary side of the 3-phase transformer. I have connected with this one winding another of the Y winding, that means the B phase winding. So, I have connected in series, it is like this comes here, then it comes here. So, I have connected this connection, I have series connection I have created such that the voltages sum upwards, phasor summation of the voltages happens, and that I have taken out and called it as A, that I have taken out to the A terminal. So, and both these sides are grounded, the neutrals on the both sides are grounded. So, the A secondary and B secondary are connected in series and then they come to the A terminal. So, I have written it A plus B goes to A dash. I did not write A because it would have confused. So, I have written A plus B goes to A dash. Now, our work usually has symmetry in it. So, therefore, I would connect B and C in series on the secondary side. Primary side very simple, there are just a star connection of the 3 primary windings, but secondary side we are adding two voltages which are phase shifted together to create an effect. So, A plus B gave me A dash, then a cyclic symmetry would say that B plus C should be given B dash and C and plus A should give me C dash. So, look at it here, B, that is the yellow phase, B plus C, the C is the blue phase, this is the blue phase, they are aligned parallelly so that our mind reads it like that. So, this and this are aligned B plus C, these two windings connected together brought out as B phase and then C plus A goes to C phase. So, the C, this C and this C are the same plus A. So, this winding corresponding this winding. So, one winding was consumed where it was consumed here. Now, where is this winding getting consumed? It is getting consumed in the C phase. So, this winding was consumed in the A phase automatically and the third winding, the tertiary winding has been consumed in the series connection in the C phase. So, connected this here C plus A and took it out as the C winding. So, this does it not look like some kind of a Z? I mean figuratively it is not, it is zigzag, it is not actually Z, but can't you see the zigzagness that we have created out of it. So, the primary is made up of only 3 windings, secondary is made out of 6 windings, but only 3 terminals come out because 2 windings each get interconnected to create the net effect of phase shift that I want and I get it out on the secondary side. Now, you can see that if I had a connection like this, even if these have some small leakage impedances and even if there are paths for currents to flow in the primary side and there are paths for currents to flow in the secondary side, because this would be also connected to some part of the grid and this is also connected to some part of the grid. We are not looking into that, but there are basically current paths to flow. Assume that there is a grid sitting here, there is a grid sitting here. So, there are current paths to flow. Still now the issue, look at it. Suppose I say that yes, even this should just behave like 3 single phase reactors which are connected from A phase to ground, B phase to ground, C phase to ground, then see the problem that I am going to have. You would then argue that this will carry some current, let us say 10 amperes at an angle 0. Let us say, just for the sake of discussion, this should then carry 10 amperes at an angle minus 120 degrees and then this should carry 10 amperes at an angle of plus 120 degrees. Then coming here because this MMF has to transfer here. So, the current which is flowing here N1 I1 equal to N2 I2 plus N3 I3, but I1 is so N2 by N1 is this. So, I1 will be equal to half of I2 plus I3 and so on. So, if this current IA comes here, this something similar will come here and this current IB comes here. So, something similar will come here, but this current is should be 120 degrees lagging A square times I A, everything being symmetric. If this is I A, this should be A square, I am sorry, if this is I A, this should be A square I A, this should be A times of I A. And so, what will happen is similar current is going to come here, but then it will get and added with what? So, I will call this as I A dash, and this will get added to what? I B dash. But this only one current can flow here, is it not? Only one current can flow here, but I A dash and I B dash are, if they are non-zero, then they are 120 degree apart. So, how can this current, same series current, become 120 degree apart and start flowing from here to here? That is simply not possible, right. So, therefore, what is effectively going to happen is that this is, I mean, if only it is 0, then it does not matter, it does not, 120 degree phase shift does not make any difference to it. So, therefore, we come to the conclusion that in this series connection, if I connect 3 balanced voltage sources here, 3 balanced voltage sources here, I will not be able to, and this is just connected 3 balanced voltage sources here, 3 equivalent same balanced voltage sources here. So, imagine that the primary side is connected to a set of A, B, C balanced sources, and I got the same set of, for the sake of discussion, appropriately scaled same set of balanced voltage sources I have connected here. Then what is going to happen is, because these currents in series cannot be phase shifted, they will have to be 0 only, that is the only right condition. So, even though I have this interconnection to ground, even though this I have interconnection to ground, under such a balanced 3 phase circuit, no currents will flow to the ground, yet they are grounded. So, this is a speciality of this connection. Then what happens is, we will not get into this further details, that if there are triplet harmonics or there are faults and things like that, then they will have smooth passage from here. So, this application is something like this, that for balanced circuits, for this transformer works like this, that for balanced circuits it works as if it is open circuited to the ground, but if there is any kind of unbalance which involves ground or needs a path to the ground, it provides path to the ground. Now, again I will come back to the apparatus. As I had said earlier, the application is a bit complicated, but the apparatus to understand is quite simple. So, to understand the functioning of the apparatus, what we have to do? We have to just calculate, add phasor superpositions we have to do of the voltages and see what is VA, VB and VC. So, I have connected A in star and the secondary side in zigzag connection. My first question to you is, what is VA, what is VA, what is VB and what is VC on the secondary side, given that this is 1000 to 1000 volts phase to ground, this is 1000 minus 120 degrees, this is 1000 plus 120 degree. So, you know that therefore, this is 500 volts, which I have marked here 500 volts at an angle 0, because this is 1000 angle 0. So, this is 500 angle 0, and this is getting connected to this yellow color. So, so this color here, which is lagging the voltage same 500 volts, lagging by minus 120 degrees. So, therefore, this I have drawn with minus 120 degrees. So, I get this angle as 60 degrees, and this is also 500, this is also 500. So, these two angles are equal, this is 60. So, that gives me 120 by 2. So, 60, 60, 60. So, I get a equilateral triangle here, and the resultant voltage that I am getting here is therefore again 500 in a equivalent. So, I am adding two 500 voltages phase shifted in such a way that the resultant voltage that I create is again 500 volts only, but it is now lagging by an angle of minus 60 degree. So, VA is 1000 angle 0 on the primary has become 500 minus 60 degrees. So, this is a different phase shift from 30 degrees. Transformers you can get Many different ways of phase shifts are possible by appropriate interconnection. This is just one more example of that. Now, let us look at VB. I will do this instead of doing it by geometry, I will do this algebraically. So, I have got 500 VB. So, for the B phase, what is this? This is 500 A square and this is C phase voltage. So, this is 500 A, where A is e to the power j 2 pi by 3, but then you can take 500 common and this becomes A square plus A, which is equal to minus 1, because 1 plus A square is 0. So, you get this as VB as minus 500 volts, which is same as saying 500 at an angle of minus 180 degree. So, you can see that A phase is 500 minus 60, then subtract 120 degree from it, and B phase is 500 minus 120. Automatically you can conclude that this will be leading, and you can verify it, will be leading by 120 degree. So, minus 60 degree plus 120 degree, that will give you plus 60 degree, and the equilateral triangle will still give you 500 volts. So, the VC will turn out to be 500 angle 60 degree. So, this is the voltage. So, the question now is, first question that I have asked is, find the 3 phase transformation ratio of this transformer. So, you have VA by this 1000 divided by 500 angle minus 60 degree. So, therefore, 2 angle 60 degree is the turns ratio. So, it is a complex turns ratio. Every time in 3 phase transformers, if you have a phase shift going from primary to secondary, ground to neutral, then the turns ratio is effectively a complex number. So, therefore, this becomes 2 angle 60 degrees. Now, let us look at the other part of the question. A 3 phase balanced resistive load of 100 ohms is applied on the Z side. Determine all the primary and the secondary load, primary and the secondary voltages and currents. So, what I have done now here, this and this is connected through some load which was impedance value was specified and then connected here. So, now the currents are going to flow, these currents are going to flow in the A, B and C, and they will get reflected and come and flow like this. So, we have to determine those currents. Unloaded, even though there was a connection to the ground, there was no current flowing, that was what I had shown earlier. Now, it is loaded, we will see that it should function as if it is a normal transformer. So, A phase voltage is 500 on the secondary side, A phase voltage is 500 at angle minus 60 degree and 100 ohms load is connected to it, resistive. So, the current will be 5 minus 60 degree. B phase to neutral is 500 minus 180 degrees. So, therefore, 500 by 100. So, therefore, 5 minus angle 180 degrees, and C phase current voltage is 500 angle 60 degrees. So, divided by 100 ohms. So, therefore, the C phase current should be 5 angle 60 degrees. This will be the balanced current, simple application of of our basic idea. Now, to translate it onto primary side, we should apply MMF balance to each of these 3 transformers. So, we will begin with this. So, N1 IA should be equal to N2 I, this one is connected to N2 small IA and this one is connected to the B phase. So, N2 IB. So, N1 capital IA should be equal to N2 small IA plus N2 small IB. This magnetizing MMF should be equal to net magnetizing MMF should be equal to net demagnetizing MMF. So, therefore, 1000 N1 is to N2 is 1000 is to 500. So, therefore, I can take N1 as 1000 because the ratios only matter. So, 1000 IA is equal to N2, which I am effectively taking. If I take N1 as 1000, I should take N2 as 500 because N1 is to N2 ratio only has matters. So, 500 times it carries A phase current, and I am sorry, probably I said yeah. So, A phase, where is it connect? I do not know what I said earlier, but let me be very clear. In this figure it is very clear. One thing carries the secondary side A phase winding current, and the other red one, what does it carry? It carries the secondary side IC current. So, therefore, this is the net demagnetizing MMF which is produced on the secondary side. 1000 times the primary current in the A phase should be equal to 500 times IA plus 500 times IC. 500 times IA is flowing here and 500 times IC is flowing here, and 1000 times IA is coming here, and this MMF should be sum of these two demagnetizing MMF. This magnetizing MMF should be equal to net demagnetizing MMF, because this is all on one transformer core, and if this is ideal, its reluctance is 0. So, whatever be the phi times of R is 0. So, I am just recapping that whatever I have done connections something peculiar on the terminals outside, the basic MMF balance principle has not been disturbed. Therefore, I get IA plus IB plus IC should be 0 in a balanced circuit. So, I get IA plus IC should be equal to minus 500 IB, and IB is how much I have calculated? I have calculated IB to be 5 minus 180 degrees. So, minus 5 amperes. So, 500 minus 500 into minus 5 will give me 2500 amperes, and then divide it by this 1000, and I will get 2.5 amperes current flowing through IA at an angle of 0, which makes sense because it is a resistive load. So, if the primary A phase voltage is taken to be 1000 volts to 0, then the current, it should be unity power factor on the secondary side. I should translate also as a unity power factor on the primary side. You could also do this by saying that N1 by IA by IA should be equal to IA by the corresponding conjugate turns ratio of the N star, which is 5 minus angle 60 divided by 2 angle 60 complex conjugate, which will be which will turn out to be equal to 2.5 amperes. Similarly, now look at it, 1000 times, 1000 is for number of turns times second IB for the B phase winding, N2 is taken as 500, and the currents which are flowing in the, this is connected one to A phase and another connection is to B phase. So, therefore, I have 1000 IB, one to A phase, one to B phase, which is minus 500 IC, which if you substitute for IC, which is 5 angle 60 degree. So, therefore, this will become minus 25 angle 60 degree, or if you divide this by 250 degree, then it is 2.5 angle, and 1 you can take it as 1 minus 1 can be shown as 1 angle minus 180 degrees. So, therefore, 60 minus 180 degrees, or in other words 2.5 angle minus 120 degrees. So, IA is 2.5 angle 0, IB is 2.5 angle minus 120, and similarly IC will turn out to be capital C, this is IC capital C will turn out to be 2.5 angle 120 degrees. So, What are some we are done basically you could see now that the we are done with calculation of voltages and currents. So, we will look at power now next step, but hard work, most of the hard work has been already done and it was not that complicated. Currents are at unity power factor. Let me make some observations. Current are at unity power factor for both primary and secondary windings in spite of the phase shift in the YZ connection. Power in primary side in the A phase winding is 1000 volts into 2.5 amperes, which is 2500 watts per phase. Power in the secondary of the A phase, I have outside terminal voltage as 500 volts, connect A to neutral, V small a to n is 500 angle minus 60 degrees, and it is connected, this is connecting with a resistor. So, V square by R, the basically power that it will dissipate is magnitude of V A square by R, which is 500 square by 100, which is 2500 watts per phase. So, you can see that the active power balance has actually happened. Now, let us check for the overall power balance for this is like effectively it is like a 2 winding transformer. So, 2500 watts per phase came from here unity power factor, 2500 watts per phase went out from the secondary side of the effective this 3 phase 2 winding transformer, but actually it is a zigzag connection. Other thing that we need to check, so this is like the black box part that I checked, but the one more thing that I want to check is whatever power goes here, complex power, the same complex power has to flow as summation of winding B and winding C, because this is my basic unit device, and you had studied in the multi winding transformer earlier that V1 I1 star should be equal to V2 I2 star plus V3 I3 star, that has to follow from the basic transformer principles that we have already discussed. So, let us check that also now. So, let us check power balance for the first 3 winding transformer. So, winding 1, let us look at it, 1000 volts is applied, 2.5 amperes at an angle 0 is flowing, V1 I1 star will be 2500 watts plus J 0, which is what is the unity power factor, we just talked about it. Now, look at winding 2, if this is 1000 volts, this is 500 and this is 500 and all the 3 are in phase. So, if this is angle 0, this is also angle 0, this is also angle 0. So, therefore, I will get V2 as VA by 2, which is 500 volts, and I2 is basically I2 I2 yeah. So, the I2 that it is see one winding was carrying A phase current, one winding here was carrying A phase current and one winding here is carrying the C phase current. So, same idea is same information has to be used. So, the I2 that it carries A phase current is phi angle minus 60 degree. So, V2 I2 star is 2500, this complex conjugate makes it plus 60 degrees. So, you can see that this secondary winding is 500 volt secondary winding is actually carrying a complex power, there is active power also in it, there is reactive power also flowing in it. Now, let us look at the winding 3, which is the winding 3 of this transformer, this is the tertiary winding. So, this tertiary winding also has 500 volts at an angle 0 and this tertiary winding carries which current? It carries IC current, because as I showed you here, one is connected in A, one is connected in C. So, therefore, it carries IC current which is 5 angle 60 degree. So, it produces V3 I3 star which is 2500 minus 60 degree. So, this also has complex power, but it is complex conjugate of this is plus angle, not complex conjugate, this is plus angle 60 degree, then this is minus angle 60 degrees. So, when you sum the total demagnet power out of the winding 2 and the secondary winding and the tertiary winding, V2I2 star plus V3I3 star will become 2500, and you have to do a vector summation of 1 angle 60 and 1 minus 60. So, 1 angle 60 is 60 degrees with respect to the horizontal line here. This is 60 degrees with respect to the horizontal line here, and then 1 angle minus 60 degrees is this line, but now taken from the tip here and at an angle of minus 60 degree, and again it creates a equilateral triangle, and therefore, this will become 1 angle 0, and so this will turn out to be just 1 angle 0. So, 2500 megawatts. So, V1 I1 star, which was 2500 J0, became equal to V2 I2 star plus V3 I3 star. Notice that reactive power exists in winding 2 and 3, but in superposition is reactive power exists in winding 2 and 3, but in superposition is cancelled in winding 1. Similarly, power balance for the other 2 winding transformers can be checked. Note that in the 3-phase transformer, if VA by VAN is capital N, then IA by IAN has to be equal to 1 by N star, and therefore, if I write VAN by IAN as ZL, then this will become N, VAN will be written as N times of this, and IA will be written as IA by N star. So, therefore, N square by this. So, effectively, hence just like a single phase transformer, when the impedance is referred from secondary to primary side, then the impedance is just scaled by the magnitude of the N square, even if N is a complex number. I think we will stop here. Thank you.